The only way to combine functions that we haven't seen yet is to compose them. So a composition of functions just means one function inside of another one. So sine of x squared, right? That's a function inside of another one, a function of a function. Square root of x squared plus 1, that's inside a radical. X to the fourth plus x to the 10th, that's a function like being exponentiated, so the exponent is the outer function in that case. With something like that, we could multiply it by itself 10 times or use the product rule 9 times technically, but we don't want to. And there's a better way, and it's called the chain rule. So it's a little weird when you first look at it, but once you see, we just have to see examples and then you'll see how it works. So here's the statement of it. Don't think of this as a formula to memorize. Just think of it as just kind of the way it works and you get used to it. So if you have capital F, which is a composition of f and g. So capital F of x is f of g of x. Then to do the derivative of big F, you take f prime of g of x. So meaning you take the derivative of the outer function with respect to the inner function and you leave the inner function alone. So notice there's just a straight up copy of g of x there. Then you multiply that by the derivative of g with respect to x. So it's f prime of g, the derivative of the outer thing, times g prime, the derivative of the inner thing. So you don't just do both derivatives and leave it. You'll see. Okay, so in this one, it's super clear what the outer function is and what the inner function is. So it's good to identify those things, at least for now. Outer function is the sine function and the inner function is x squared. So in the first step, you're going to deal with the sine function, meaning take the derivative of it, but leave the inner function alone. Right, so it's cosine of x squared and the x squared is just there. So it's a copy. It's a copy of the inner function that's going to appear in your answer. The derivative of the inner function is easy. That's 2x. So you take f prime of g and you multiply it by g prime. So it's cosine of x squared times 2x. That's the final answer. And I'll say this over and over again. It's not just cosine of 2x. To prove the chain rule takes some pretty higher mathematics. So you're just going to have to kind of take my word for it that that's how this works. Okay, and any inner function, we'll do this for not just a function of a function, but like 3, 4, 5 functions nested within each other. You're always going to end up with a copy of anything that's inside in your final answer. I change it to x cubed, so this is the square root of x cubed plus 1. This doesn't simplify in any meaningful way, so it's obvious that the outer function is the radical and the inner function is x cubed plus 1. So let's make that clear. Anytime you have a radical, you want to rewrite it as a fractional exponent, so you can just use the power rule on it. Identify, you won't always have to do this, but for now say, okay, obviously the thing that's happening to everything is the square root, and then the thing that it's happening to is the x cubed plus 1. When you deal with the outer function, you're just using the power rule, so it's 1/2 x cubed plus 1 to the negative 1/2. You're just treating x cubed like plus 1 plus a variable. You can call it u and just say, okay, the derivative of the square root of u is 1/2 u to the negative 1/2. It just comes with. And then g prime again is easy. The 1 goes away, so it's just 3x squared. So you just multiply those two things together. All right, the derivative of the square root of x cubed plus 1 is 1/2 x cubed plus 1 to the negative 1/2 times 3x squared. So on the next exam, that would be a perfectly acceptable way to leave it. We can clean it up a little bit in a common sense way just by putting it back to radical form. That just looks nicer, but you don't have to do it. You can leave stuff with, negative exponents and whatever. So that just looks better to me. Again, I'm emphasizing that a very common mistake is just to think that it works like the sum rule works, where you just do the derivative of everything separately. It doesn't. The more complex a function is, the more complex its derivative is. So something like sine of x squared is a complicated function, so its derivative is even more complicated. All right, so that's what not to do. It's not cosine of 2x, and it's not just 1/2 3x squared to the negative 1/2. That's how you want it to work, but that is not how it works. So just always remember you do get that copy of the inner function. Sometimes it's not as clear what the outer function and the inner function are. So if we have something like cosine to the 8th, it's always good to remember what that really means and then to rewrite it that way as well. So, right, this is cosine times itself 8 times, so we could just use the product rule. We've used the product rule more than once. We could use it 7 times, but we don't want to. So that's what that really means, right? Cosine to the 8th of x really means cosine of x to the 8th. So if you write it like that, you don't have to, but if you do, it's more obvious that, oh, the exponent is the outer thing, right? That the power of 8 is our f, is our outer function, and then cosine is the inner function. If you see it the first way, that's not as obvious. It's just notation. You deal with the outer function, which is the power of 8, so that's just power rule. It's 8 times whatever the inner function is to the 7th, so leave that cosine alone in that step, then multiply by the derivative of cosine, which is negative sine. So that's negative 8 cosine to the 7th of x. You can leave it like cosine of x to the 7th. It's the same thing. Then times sine of x. So you see what I mean? The more complicated a function is, like something like cosine to a big power, the more stuff is going on in its derivative. It's cosine to a big power and then times sine times negative 8. So just another just specific case of the chain rule. This isn't a new formula that you have to know or anything. It's just something you notice after doing it a bunch. If you have a function to a power, then the derivative of that is always the power times the function to the power minus 1 times the derivative of the function. It's just something you see a lot in trig, especially, is like sine and cosine to powers. That's just, you can see that that's always just what it ends up being. So that's just a specific instance of the chain rule. And let's use that again. So now we have a quotient to the power of 10, right? We don't want to use the product rule 9 times. We want to just use the chain rule. So leave the inner thing alone. So first the power comes down and then goes down by 1. So it's 10 times x squared minus 1 over 2x plus 1 to the 9th times whatever the derivative of x squared minus 1 over 2x plus 1 is. Okay, and I'm not writing out every little step here, so it's the original thing times, okay, the bottom times the derivative of the top, which is 2x plus 1 times 2x, minus the top times the derivative of the bottom, which is x squared minus 1 times 2, all over the bottom squared, 2x plus 1 squared. So again, I know that you're tempted to try to simplify that, to actually multiply that stuff in the numerator out. I don't blame you for that. That's a good instinct, but I would ask that just leave it like this. That's a fine way to leave it. It's not like we're doing anything with this. This is the whole problem. It's just to find a hard derivative. So that's a fine answer. So we're getting a little closer to the kind of stuff you're actually going to be seeing on quizzes and exams coming soon. These are derivatives that are just hard just because. Just to make you learn the rules. So secant of tan of the square root of sine. This is 4 functions inside each other. So it's just important to proceed in order. Secant is the first thing, tangent is the second thing, the square root is the third thing, and then finally sine is the innermost thing. Sine is inside of everything else. So we're going to have to use the chain rule 3 times. So it's important that you just stay organized. You're going to get to a point where you can almost do these in your head. Like there's no work to show. You can just jump to it, but take your time with it for now. You'll get there. I know it looks crazy. The first thing that's weird is that, remember the derivative of secant? Of course you do. It's secant times tangent. So there's actually 2 x's in there. So what we're going to see with secant is a weird one because we actually have two copies of that inner function. So the derivative of secant of tangent of square root of sine is secant of tangent of square root of sine times tangent of tangent of square root of sine. That's easier written than done. All right, so the first step is kind of the weird one because secant has that weird derivative where there's two x's in it. So it's secant of all the inner stuff times tangent of all the inner stuff times the derivative of the inner stuff, and then you just keep working your way in. So with every step, this thing gets bigger and bigger and bigger. So it's just times the derivative of tangent of square root of sine. So we get two copies of the original inner function, which is tangent of square root of sine, in our answer. And we just keep working and deal with it. So do it one step at a time. Don't get overwhelmed. Just do one derivative at a time, and you know how to do that. So it's the beginning thing, leave that alone. The derivative of tangent is secant squared. So the derivative of you're right. So the derivative of tangent of square root of sine is secant squared of square root of sine. And then you're moving in one more time, multiplying by the square root of sine. I'm sorry, the derivative of the square root of sine. And remember, that's sine to the 1/2. So that's kind of the same as like when we did cosine to the 8th. That's a trig function to a power. All right, so that's all that stuff that we already did. Times, first you deal with the square root. You don't deal with the sine yet. The derivative of the square root of sine is 1/2 times sine to the negative 1/2. Finally, times the derivative of sine. All right, so it's secant of tangent of square root of sine of x times tangent of square root of sine of x times secant squared of square root of sine of x times 1/2 sine of x to the negative 1/2 times cosine of x. Nasty, right? If you didn't know any better, you'd think like, what kind of math is this? Again, there is obviously a practical use for all this stuff, but I'm just throwing hard stuff at you now. So this is actually exactly like the next exam is really mostly just hard derivatives. And this is really this is the level. Like we're at the level now of stuff that you're going to be tested on. So if you can look at that hideous thing that's in front of you and be like, okay, I see where all that came from, you're in good shape. Let's do one more nasty one just to practice. So at this point, just pause the video and try and do this one yourself, right? And then, see if we arrive at the same conclusion. So again, let's just identify what's what. It's really cosine of all that stuff to the 4th. So the power of 4 is the outer function. It doesn't look like it here, but that's why it's good to rewrite things like cosine of that stuff, all that to the 4th, because that's acting on the whole thing. So the first thing you deal with is the power of 4, not the cosine. It's 4 times cosine cubed of all that inner stuff, and then we deal with the cosine. So you leave the cosine alone in that first step, and now you deal with the cosine and you leave the sine of x over x cubed alone. The derivative of cosine is negative sine, so it's all the first stuff times negative sine of x over x cubed, and then times the derivative of sine of x over x cubed, which is quotient rule. You should basically be able to do the quotient rule more or less in your head at this point. So it's 4 cosine cubed of sine of x over x cubed times negative sine of x over x cubed times the quotient rule, which says, okay, it's the bottom times the derivative of the top, so x cubed times cosine of x, minus the top times the derivative of the bottom, so sine of x times 3x squared all over the bottom squared, so x cubed squared. You can leave it like that. This one, to me, sort of cries out for a little bit of simplification, just because if you look at that very last term, you have an x cubed and a 3x squared and an x to the 6th. So you can take at least an x squared out of everything there. And then I also just think it looks funny to leave the negative sign in the middle of it, even though it's not wrong. It just looks nicer to me to bring the negative sign out front. So if you're ever not clear, just ask, but you can leave it as messy as you want to. Okay, so just bringing the negative sign out front, -4 cosine cubed of blah blah times sine of blah blah times, so in that last term I just zapped an x squared out of every term. So the x cubed became x, the x squared went away, and the x to the 6th in the denominator became just an x to the 4th. And that's as good as it's going to get. So never expect that these are going to clean up in any meaningful way. It's only in certain instances, like you'll see with logs, that it actually does simplify in kind of a cute way. But for now, assume that if I give you a messy function, it's going to have an even messier derivative.